This is the second section of the Taylor series chapter, and this is all about finding limits. So in this section, we're going to be looking at find a limit as x in the function tends to some value. Now we're probably used to doing these types of questions, maybe where it's the limit as x tends to 0 or x tends to infinity. And what we need is an algebraic way of doing these types of questions. So for example, it may be the limit as, I don't know, x tends to infinity of, let's say, 3x plus 2 over x minus 5. Okay, and we want an algebraic way of working, well, what is that? What does that limit become? Well, before we look at that, we're going to look at some rules to do with limits, because if we can work out the limits of individual functions, we can actually use those individual limits and put them together. So for example, let's take two functions. Let's call one function f of x, and let's call the limit of that function as x tends to some value a. Let's say that the limit of this, we'll call it L, alpha limit. And let's say we've got a different function. Let's call that g of x. And again, the limit as x tends to a, so the same value. Let's say the limit of this is m. Now, what we've got are rules, and they're called the algebra of limits. The algebra of limits. In other words, the rules for limits. So what do these rules look like? Well, the first rule is that if I have the limit of the first function as it tends to a plus the second function, so actually we're almost like putting these two functions together first before we find a limit of them. So let's put some brackets in them, brackets here. So it's the sum of the functions, and we find the limit of that. Well, that's just equal to the sum of their limits, so L and M. So we sum the function, find the limit of that sum of functions, and it's equal to the sum of the limits of each individual function. Okay, so that's like almost like the addition rule. Okay, now if I've got my function f, let's say that I multiply it by a constant, let's call it, say, a constant k. So I've got the limit as x tends to a of this function, which is basically a multiple of my function f, and you could probably guess that actually the limit is going to be a multiple of the function of f. Okay, so you could almost think of this like the multiplication rule, where you sort of multiply your function by a constant, so you multiply the limit by a constant. Okay, last one. Let's say that I've got the product of my functions f and g. Okay, so let's put that there. So working out the limit as x tends to a of those two functions multiply together, and you can probably work out that it's going to be their limits multiplied. So that's more like the multiplication rule than the previous one. I suppose the last one's like the constant rule. So you could think of this like the addition rule, the constant rule multiplying by a constant, the multiplication rule. Then the last one, the only thing that's missing is like the division rule. So as I have the limit as x tends to a of one function divided by the other, like that. So, well, that's going to be actually the limits divided by each other. Now, because dividing by 0 is not defined, we can't divide, or m can't be 0 if m is not equal to 0. That rule applies. If m does equal to 0, then we need to go back to the drawing board. So we've got these rules for our functions here and the limits of those functions. So we can add the limits together when the functions are added together. If the functions multiplied by a constant, we multiply the limit by a constant. If we've got a product of two functions, then we find a product of their limits. If we've got two functions divided by each other, we divide their limits by each other, as long as the limit of this function here at the bottom is not equal to 0. Okay, here's some hints then for doing these types of questions. So the first one is that we want to avoid this type of situation. The limit as x tends to infinity of some sort of function of x. Let's call this kx, because actually that's just going to go off to infinity. And the way that we can avoid that is by dividing the whole expression through, because that's only going to be part of it, through by x. So if we divide the whole expression through by x, we're still finding the limit as x tends to infinity, but it's going to be something like k over x. And we know what happens when x tends to infinity there. That fraction is going to tend to 0. Yeah, so this is, I'll write this over to the side, this is something they will assume that you know. The limit as x tends to infinity of 1 over x is 0. Second little tip is if we see, let's say, sine x, cos x, log x, okay, if we see any of those in the expression that we need to find the limit of, we're going to use a Taylor series expansion for these. Okay, so if we see any of these, so what we would do is we would replace with the Taylor series expansion about a. So a is going to be the limit. So for example, let's say I needed to find the limit as x tends to 3 of, let's say, sine let's say x squared minus 9. Okay, so you can see really as x tends to 3, this is going to tend to 9, and we're going to get like sine 0 and sine 0 0, so that's no good. We can actually write that as a Taylor expansion of sine about 3. So we do it about the limit that we're trying to get to. So I'll just write that down. So yeah, here we're going to write the Taylor series expansion for sine x about 3. So we know that in a Taylor series expansion, that means that A is going to be 3. Okay, so here we've got find the limit as x tends to 0 of 5 minus x over 2 plus x. So here we're going to use the algebra of limits, and the algebra of limits says that if I want to find the limit as x tends to a of a function over another function, then I divide the limits. Yeah, so L is just the limit of function f, and M is the limit of function g of x. So that's what we're going to do. So we'll start with the limit as x tends to 0 of 5 minus x. Okay, so, well, I can see that as x tends to 0, that's going to tend to 5. So that's on my f of x. Then we'll have a look at the limit as x tends to 0 of 2 plus x. And again, I can see that as x tends to 0, this is going to tend to 2. So using the algebra of limits, this will just become the limit of f divided by the limit of g, function at bottom. So there we go. 5 over 2. Now, if we look at this one, there's a problem. We want to avoid, if you look at the introductory slide, this type of thing, where we're doing basically something that's tending off to infinity. So I'll just write it down again. So you want to avoid things like the limit, particularly when x tends to infinity, of something times x, not multiple of x. And the way that we can avoid that is by dividing everything through by x. So we're going to do that. So finding a limit of x tends to infinity of 2 minus 3x over 1 plus x is the same as or equivalent to the limit as x tends to infinity. If we divide every term through by x, then we'll have 2 over x minus 3x over x. Let's write that down, and I'll simplify in a moment. Over 1 over x plus x over x. Right, so we can simplify that. So the limit as x tends to infinity now will become 2 over x. We can evaluate that. 3x over x will just become 3. And then we have 1 over x, we can evaluate that, plus 1. Now what's going to happen is that as x tends to infinity, that's going to tend to 0. The 2 over x, anything over x is going to tend to 0. And the same here, that is going to tend to 0. So just like before, we're using the algebra of limits. So we're going to look at the limit. Strictly speaking, we should do this. The limit as the numerator tends to 0. So 2 over x minus 3. So that will tend to, or that will equal minus 3. And we'll look at the limit of the denominator as x tends to infinity. So that would be 1 over x plus 1. So the 1 over x, as we say, tends to 0. So that's going to tend just to 1. So using the algebra of limits, what we'll have is the limit of the numerator divided by the limit of the denominator, which just becomes 3. Okay, now in this question you can see that we have this sine x at the top. Now whenever we see sine, cos, log x, anything that we can differentiate an infinite number of times, and the value of that differentiation at a particular value a can be evaluated, then we can use the Maclaurin or Taylor expansion. So it's the Taylor expansion. Let's spell his name right, not Taylor, Taylor. Taylor expansion of sine x at, and it's always at where the limit is going to, so at 0. But we know that when we do the Taylor expansion of anything at 0, that's basically the Maclaurin expansion or Maclaurin series. So that makes things easier because we can just use the Maclaurin expansion that's given in the formula book. And that is this. In the formula book it will tell you that sine x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. I don't know if it says that, but you can work out the pattern. So we don't actually need to differentiate it and work out the Taylor or Maclaurin expansion from scratch. We can just use that. So this is what we will use. So the limit as x tends to 0. So sine x we will write as x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus dot 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 minus x over all over x cubed. So what we're going to do now is just use some algebra to simplify this. So you'll notice that we've got x minus x, they're going to cancel out. And then we can divide every term by x cubed, can't we? We can divide all of these, divide that by x cubed, divide that by x cubed, divide this by x cubed, and so on. So if we do that, so obviously the x's are gone. So now what we've got is 1 over 3 factorial plus x squared over 5 factorial minus x4 over 7 factorial plus dot dot dot. Just realised I missed out a minus sign here. So let's put that in because I had a minus sign from before. I think all the other signs are correct. So what's going to happen as x tends to 0, then obviously that tends to 0. So these fractions tend to 0. So all that leaves is the negative 1 over 3 factorial. So the limit as x tends to 0 is going to be negative 1 over 3 factorial, which is negative a6. So we could say that our limit, so answering the question, as x tends to 0 of sine x minus x over x cubed equals negative a6. So there we use the Taylor expansion of sine x at 0, which is basically the Maclaurin expansion, to replace sin x with this series expansion, and then the rest is just algebraic simplification. Now, what we'd want to do is replace this tan x with the Taylor expansion for tan x at, well, be at pi over 2. But there's a problem. To do any type of expansion, you need to be able to differentiate an infinite number of times. And with tan x, we can do that because you differentiate tan, it becomes x squared, and you can differentiate x squared, so that's not a problem. But you also need to be able to evaluate that function at a particular value. So what we need to be able to do is to evaluate all of the derivatives at pi over 2. But as soon as we try, well, let's write out what the Taylor expansion would look like. So if we started to try and do that tan x, so that would be, first term would be f of a, so tan of pi over 2. Well, straight away, we run into problems. We can't go any further because that is where there's an asymptote. So tan of pi over 2 is not defined. So we cannot use the Taylor expansion for tan x at pi over 2, because as soon as we try and evaluate it, tan of pi over 2 on our calculator is going to come up error. So we need to use a different method. And this is where I'd use a trig identity. And what I can do, I can replace tan x with 1 over cot x, because I will be able to evaluate cot of pi over 2. It is defined at that point. So sometimes on these types of limit questions, if you're not able to evaluate or write a Taylor expansion for a trig, something like that, at a certain point, use a trig identity and see if that works. That often solves the problem. So the question, which started like this, the limit as x tends to pi over 2, x minus pi over 2 tan x, now becomes the same limit as x tends to pi over 2, and x minus pi over 2, but now times by 1 over cot x. This is equivalent. Yeah, so we're going to evaluate this, which means we want the Taylor expansion for cot x about pi over 2, which we can do because cot of pi over 2 is going to be, from memory, 0. So it can be evaluated and it can be differentiated. Right, so let's start by reminding ourselves of what the Taylor expansion is of a function, and that is f of a plus f dash of a times by x minus a plus f double dash of a times by, well, this is all over 2 factorial, put it here, or under the x minus a all squared, plus, let's just do one more, f triple dash of a over 3 factorial x minus a cubed, and so on. So let's start with f of a, so that will be cot pi over 2. So our function, let's just say, right, so f of x is cot x and a is pi over 2. Right, so cot x can be written as cot, so this is f of a cot of pi over 2, and then we need to differentiate cot, so let's put a little space over here to work out all our derivatives. So f dash of x will be cot differentiated. Now this is in the formula book, and it tells us that when we differentiate cot kx, we get negative k cosec squared kx, so k is 1, so it basically becomes minus cosec squared x. So now we need to evaluate that at pi over 2. That's like f dash of a. So that's going to be negative cosec squared pi over 2. So obviously there's no pi over 2 button. So we'll just do negative 1 or negative sine 1 over. This is what we'll put on our calculator. 1 over sine squared. We're basically doing this on my calculator. So I'll just evaluate that. Put those squared in here, forgot that. Yeah, this actually works out here just to be negative 1, because sine pi over 2 is just going to be 1. So we've got basically 1 squared at the bottom. So negative 1 over 1 squared is just negative 1. Okay. Let's work out the next derivative. So here we can use the chain rule to differentiate the cosec squared. So yeah, using the chain rule, it will become negative 2. So we like differentiate the outside. I hope I'm leaving myself enough space here. So power 1. And then the inside, well, it doesn't change. That's still going to be negative cosec squared x, and yeah, we're going to multiply by the, so it's not cosec squared, it's just cosec x. Then we're going to multiply by that differentiated. Now actually in the formula book, again, cosec is given as negative cosec cot. So since it's negative cosec, it's just going to become cosec cot. So times by cosec x cot x. So we can tidy that up, and we'll get to cot x. Not sure why I'm putting squared again. So cot x cosec squared x. And again, we're going to evaluate what this is at pi over 2. So this will become 2 times by cot pi over 2, which is 0, so the whole becomes 0. And then interestingly enough, this bit here at pi over 2 we worked out, didn't we, before? We did that here. Yeah. So it would actually be 1, so we can use that previous answer, but no point because the whole thing just becomes 0. And we're going to do one more, do the third derivative. So here we'll use the product rule, where we have cot x as one part of the product, or 2 cot x as one part of the product, and the other part of the product has the cosec squared x. So we're just using product rule. So like with u and v, so we will have cot x, we'll call that u times by v dash, which is cosec squared differentiated. And we can use our first result to work out what cosec squared differentiated. We know what negative cosec squared differentiated is. It's this. So cosec squared differentiated is basically going to be this with a minus sign in front. So I will probably put a times and another set of brackets. So that'll be minus 2 cot x cosec squared x. So that's like my u v dash part of my product. Plus, now I want to differentiate cot x, and cot x differentiated, just remind myself that's going to be minus cosec squared x. So plus minus cosec squared x times by v, which is just the cosec squared x. So I think we just need another bracket there. So as usual, I've run out of space. So what I'm going to do is to write what this expression is, simplify. Let's do it over here. So that will become minus 4 cot squared x cosec squared x minus 2 cosec to the power 4 x. Yeah, so that's what all of this will become when we expand out the brackets. So we now want to evaluate this at pi over 2. So it's going to be minus 4 times by cot pi over 2 squared. Now cot pi over 2 is 0, so it's going to be 0 squared. Now it's going to be 0, but I just want to show you cosec squared of pi over 2. Now we've worked that out before, haven't we? Cosec squared of pi over 2, so it's not going to be negative 1, because that's negative, it's going to be plus 1. So we can put times by 1 here, but obviously that becomes 0, minus 2 times by cosec squared, or cosec to the power 4, which is basically cosec squared squared. So we know that cosec squared is 1, so it's like 1 squared. That's cosec squared to the power 4. So all of that just becomes negative 2. So the bits we're interested in are these numbers here. Let's just highlight them. That's going to give us those coefficients. Right, so now we can go back to what we had before, and actually I'm going to rub this out because I've sort of worked these things out already. So cot x, and all of this just to find a limit. Cot x, right, that's going to be cot, I don't know why I did rub it out, cot of pi over 2, that's f of a, we'll work that in a minute, plus f dash of a, now what was that? That was negative 1, times by x minus a, so that's x minus pi over 2, plus, okay, f double dash of a, which was 0. So we've got 0 over 2 factorial times by x minus pi over 2 squared, plus f triple dash of a, which was negative 2. So it's negative 2 over 3 factorial x minus pi over 2 cubed, plus dot dot dot. Right, now let's simplify this. So first of all, cot of pi over 2 is 0, so we don't need to write anything down. Then this is going to be negative, and then x minus x pi over 2. the next term, well, that all disappears because we've got 0 times it by 0. Then the next term, we will have negative 2 over 3 factorial, which is like negative 2 over 6, which becomes negative a third. So minus a third x minus pi over 2 cubed. Right, after all of that, we can go back actually to the original question, which was evaluating a limit. And remember, the reason why we couldn't evaluate this limit was because we could not write a Taylor expansion for tan at pi over 2. So we did it as cot. So what do we have at the numerator? X minus pi over 2. Then in the denominator, now we've got the Taylor expansion basically for cot x at pi over 2, which is this. We've just gone up to the x cubed term. That's normally as far as we need to go. Okay, so it's this. Now we can cancel this down because we can divide each term in the denominator by x minus 2. So that will just leave 1 at the top. And then at the bottom, if we divide this by x minus pi over 2, I think I said x minus 2, I meant x minus pi over 2, this just becomes negative 1. This here, this will just drop down by 1 power, so minus a third x minus pi over 2 squared now. Now what's going to happen is, as x tends to pi over 2, this bracket here is going to tend to 0, and so will all the subsequent brackets, because they're all going to have x minus pi over 2 in them. So they're all going to disappear. So the only thing that's going to be left is the 1 and the negative 1. So the limit, all of that, just to tell us that the limit is going to be negative 1. Okay, so on this question here, it's the log x that we need to write the Taylor expansion for, about 1, and we know it's about 1 because that's the limit where x is tending to of log x. So let's create some space over here and do that over this side. So we know that in a Taylor expansion we're going to need each of these evaluated at 1, f of x, f dash of x, and so on. Actually, let's write down the Taylor expansion, and there it is like magic there. So we can now continue with what we're doing. So yeah, f of x is log x, so f of 1, remember a is 1 in this, a equals 1. That will be log 1, and log 1 is 0. Let's differentiate log. We should know what log differentiated is. That's 1 over x. So we want f dash of 1, which is going to be just 1 over 1, which is 1. Let's differentiate 1 over x, which is the same as x to the minus 1. So that becomes minus x to the minus 2. So f double dash of 1 will just become minus 1. And then we'll just do the last one, third derivative. So that will be 2x to the minus 3. We'll evaluate that at 1. So that just becomes 2. So these are the numbers we're interested in. Let's just highlight them: 0, 1, -1, 2. Right, so now we can write the Taylor expansion for log x. So log x is going to be equal to f of 1, which is 0, plus f dash of 1, which is 1, times by x minus a is 1, plus -1 over 2 factorial x minus 1 squared, plus, then we're going to have 2, that's f triple dash of 1 over 3 factorial x minus 1 cubed. So we'll simplify that and we'll have x minus 1 minus a half x minus 1 squared plus a 6, that's 2, no, not a 6, that's going to be 2 over 3 factorial, so 2 over 6, that's a third, x minus 1 cubed. So now we go back to our limit. So we always do this, we've got log, sine, tan, these types of things, we always replace it with the Taylor expansion. So we're going to have 3 times the expansion for log, which is x minus 1 minus a half x minus 1 squared plus a third x minus 1 cubed. Now, interestingly enough, if we have a look at the denominator, which is x squared plus 2x plus 3, or minus 3, guess what? It factorizes to give us x minus 1, that's handy, and x plus 3. So some cancelling down. So let's just write that down to the bottom. X minus 1, x plus 3. So what's going to happen? This will cancel with this, and that power, and this power will become 2. So what are we left with? Now the limit as x tends to 1 of this. So it will be 3 times by negative, oh no, sorry, it'll be a 1 there, won't there? It won't just disappear completely. So yeah, it'll be 1 minus a half x minus 1 plus a third x minus 1 squared all over x plus 3. Now as x tends to 1, all of these terms here, they're all going to become 0, aren't they, in the brackets, and all the subsequent terms after it, they're all going to become 0, they're all gone. So what I'm left with at the top is basically 3 and then the 1 in the bracket. The bottom, as x tends to 1, well, that's going to tend to 4. Yeah, so we just use our algebra of limits. So I can now say that the limit as x tends to 1, well, this is 3/4, by the way, of 3 log x over x squared plus 2x minus 3 is 3/4. There we go. So you should now be able to do exercise 6b on pages 138 2139. So just to recap, what have we got? Well, we've got our algebra of limits. So we've got when we can find the sum of our limits. So if I'm finding the limit of one function plus another, so here what we've got is the limit as x tends to a of one function, let's call that L, and the limit of a different function, we'll call that limit M. So if we're finding the limits of these two, we can just add their limits together. So let's put in limit as x tends to a. We've got like one where we've got like a constant. So if I'm finding a limit as x tends to a of a constant times a function, then I can just times its limit by that constant. I've got the multiplying rule, which says if I've got the limit of one function times by another, then I can just multiply the limits, and this is like the division rule. If I've got the limits where I'm dividing one function by another, I divide the limits, but we need to watch out here that m cannot be equal to 0. So there's our algebra of limits. We talked about how we want to avoid finding a limit as x tends to a of, let's say, something like this, and the way that we can deal with that is to divide through by x, and also when we have sine x, cos x, log x, etc., then we'll use the Taylor expansion of the function about a, and a will be what x is tending to.